Hello everyone. In our last couple of lectures, we saw that sharing global data between multiple threads could cause race conditions or indeterminate behavior, which is bad. So we need to avoid that indeterminate behavior or race conditions. And to do that, we said that we have to implement mutual exclusion so that only one thread can enter its critical section at any given time. And in our last lectures, we saw that locks are constructs provided by the operating systems which help us achieve this mutual exclusion. We can protect our critical sections by locks. Okay, every thread, when it enters critical section, first it has to acquire a lock, and only then it can enter the critical section. And after finishing the critical section, the thread can release the lock. And when one thread is holding a lock, no other thread would be able to enter the critical section, because if another thread tries to acquire that lock when one thread is already holding it, that second thread would block. Okay, so its acquire function will not return until the first thread has finished its critical section and released the lock. Only then the lock will be given to the second thread, and then the second thread lock or acquire function will return, and it will be able to enter the critical section. Okay, so that's what we studied in our last lecture video, and in this lecture, which was about the use of locks. Okay, how to use locks to achieve mutual exclusion in our code. In this lecture video, we'll continue with this, but we'll go a level down and we see how locks are implemented by the operating system. Okay, so how does the operating system guarantees in its implementation of the locks that only one thread is able to acquire the lock at any given time. Okay, so how does the acquire lock and release lock functions are implemented? So for this implementation, usually the operating systems have three goals. First and foremost is correctness. Okay, so that the implementation is correct and it is able to achieve mutual exclusion. Okay, if the application is incorrect and there are bugs, and in some cases mutual exclusion is not achieved, then all the other goals are of no importance. Okay, so first and foremost, the most important goal is correctness. Okay. Second goal is fairness, that implementation should be said that if multiple threads are trying to acquire a lock, correctness guarantees that only one thread will be able to acquire a lock. Other threads will be waiting. Their acquire function will block and it will not return, and it will wait until the lock is released. So fairness is another criteria which is similar to fairness in scheduling, that eventually every thread waiting for a lock should get a lock. Okay. It should not happen that one thread is waiting indefinitely and other threads are getting the locks continuously. Okay. So fairness is another criteria. And third criteria, which is also important, is performance. The implementation should not be too slow. Okay. If the implementation is slow, then all our programs would become slower because of this locking and unlocking. So it should be efficient and it should work on single processor with single thread, single processor with multiple threads, and multiple processor with multiple threads. Okay, it should work on all of them in terms of correctness as well as performance. So on a single processor, if there's a single thread program, usually I hope you can guess that race conditions do not arise, because race conditions arise when there are multiple threads sharing global data between them. Okay, so this case is already checked. So we have to guarantee our implementation on multiple threads cases, both on single processor as well as multi-processors. So let's see how operating systems implement locks. We'll see a few implementations, not one implementation, but more than one implementations. And so we'll see that there are different ways to implement locks on different architectures processes. So first we'll start with a couple of naive attempts which seem correct on the face of it, but which might have bugs or correctness issues. Let's go. So we know that race conditions happen because scheduling is not in our control. Okay, so threads can be scheduled and descheduled at any time by the scheduler, and scheduler basically gets help from the hardware for context switching. If you remember, we studied that there's a timer interrupt that comes, and then control is transferred to the OS scheduler, and OS scheduler then deschedules one thread and reschedules another thread. So one option could be that since all this scheduling is happening because of interrupts, we can perhaps disable the interrupts while we are inside our critical section and re-enable the interrupts after the critical section. Okay, so in that case, the acquire lock function would look like this. Before entering the critical section, we would disable the interrupts, and once the critical section has been executed, we'll call unlock, and that would enable the interrupts. Okay, so we'll protect our critical section by disabling and enabling interrupts. So let's say if one thread is running and it wants to enter the critical section, it calls this lock function, interrupts are disabled, and this thread now enters the critical section. Now, since the interrupts are disabled, we are guaranteed that this thread will not be descheduled from the processor, because since there's no interrupts, there will be no timer interrupt, and since there will be no timer interrupt, scheduler will not be called until we enable the interrupts, and that would happen only after we have exited the critical section. Okay, so we are making sure by disabling interrupts during the critical section that no other thread enters its critical section during the time when we are in our critical section. Okay, so every CPU has special instructions for disabling and enabling interrupts. So if we implement our lock and unlock functions with these special instructions, disable and enable interrupts, then we can achieve critical section, but only on single processor systems. Okay? On single processor system, since only one thread is running at any given moment, so let's say it is our thread which is entering the critical section, so it will disable the interrupts and it will enter the critical section. Okay? Now, since there's only one processor, so no other thread can run until this thread has been descheduled. And this thread cannot be descheduled because interrupts are disabled, and it can only be descheduled after it enables the interrupts. Okay? So on single processor system, it works, but on multi-processor system, this implementation will fail. Okay, it will not be correct. The correctness parameter will fail on multi-processor system, because let's say you have two threads that are accessing critical sections and are following the same protocol, calling lock and unlock before and after the critical section. So these two threads are running on two different parallel processes, and they are running simultaneously. And let's imagine that for whatever reason, they both call lock simultaneously on two different processes. So they both will basically disable the interrupts, and both will enter the critical section. They both will enter the critical section simultaneously, and that will violate the principle of mutual exclusion. Okay, so two threads are in their critical section at the same time, so it will cause race condition, and this implementation fails the correctness parameter on multiple processor systems. Okay, so again, this is not correct implementation. And secondly, another problem with this implementation is that while interrupts are turned off, interrupt is a privileged operation. Like these special instructions, they are privileged instructions which can be executed only in the high privilege mode, which is accessible only to the OS. But let's say somehow you are able to perform these instructions through the OS. The problem is interrupts are there for a reason. There are very important interrupts that inform the operating system about different events. So when we turn off the interrupts during our critical section, all the useful interrupts, if they arrive, they will be lost. Okay? Since the interrupts are off, our processor will not be notified of these interrupts. Okay, so they can be lost. So this strategy has multiple problems. It is not correct on multiple processor systems, and also it can result in loss of interrupts. Okay, but it works on single processor systems. It has only limited utility. So this was our first implementation of locks, the implementation of acquire and release functions, which we saw that is not correct. Let's try another implementation for the same acquire and release functions. In the second implementation, we will use a global variable, a flag, to communicate between threads. So here is an implementation. So we have this structure lock underscore t, and inside it there's a flag, okay, and this is the type of the variable lock underscore t. So when we want to use a lock, we will define a variable of lock underscore t, and we'll call lock and unlock on that variable. So init function, to initialize this lock, we'll initialize it to 0. Okay, we'll set the flag to 0. So basically, you remember lock had two states, free or locked. So when the variable is equal to 0, flag lock is available or it is free. And when variable flag is equal to 1, it means the state of lock is now acquired or it is being held. Initially lock is free, so we initialize flag to 0. In our lock function, the implementation of our acquiring the lock function, we basically see if the value of flag is 0 or not. If the value of flag is 0, it means lock is free. So this loop will basically, this is an infinite loop, while not infinite, but it's an empty loop, which will run or continue running until value of flag is equal to 1. So while value of flag is equal to 1, this empty statement, it does nothing, and we continue running the loop. So when the lock is free, value of flag is equal to 0, so this condition becomes false, and this loop is terminated immediately. And we make the value of flag equal to 1, and this lock function will return. Okay, so whichever thread called this lock function initially, since the flag was 0, now that thread has acquired the lock. Okay, because now value of flag is 1, and lock function for that thread has now returned, and it can now enter the critical section. While that thread is in critical section, let's say another thread tries to acquire the lock. So it will also call this lock on the same variable, and it will enter this loop, and it will see that the value of flag is equal to 1, and this condition is true. So this loop will spin. This loop will spin, and it will continue spinning until the value of flag is 1. Okay, value of flag is 1 because another thread has already acquired the lock, and that thread is now holding the lock. So as long as that thread holds the lock, this flag value will be 1, and this second thread, its lock function will not return, but it will be stuck in this loop here, and it will wait for that thread to release the lock. Okay, so the second thread will not be able to continue in its critical section because its lock function will not return until flag is equal to 0. So it will spin, and ultimately the first thread will release the lock. It will call unlock, and unlock will make the value of flag equal to 0. It has released the lock. So now it has released the lock. So the second thread, which was waiting for the flag value to become 0, again, it will basically see that now the flag value has become 0. This condition has become false. It will get out of the loop, and it will make flag 1 and enter its own critical section. Okay. So now if the third thread comes and tries to acquire the lock using this function, it will block because now the second thread has acquired the lock by making flag 1, and now it's in critical section. So the third thread will wait until the second thread releases the lock. Okay. So try to think whether this implementation has some issues or not. Will it work on single thread processors, single core processor? Will it work on multi-core processor, both in the case of multi-thread programs? You pause the video here and give it some thought whether some problem can happen or not during the execution of multiple threads on a single core processor or on multi-core processor when trying to achieve mutual exclusion by this implementation, calling lock and unlock with this implementation. So pause the video and think about it. I'll continue further with the solution to this question. So this implementation, on the face of it, it seems correct, but it can have some problems. Let's talk about single core processor. In a single core processor, let's say two threads, they try to call lock simultaneously. Only one of the thread will be running at any given time because it's a single core processor. So here it is. So the thread 1 calls lock, and while flag equal to 1, it checks for flag value. Let's say flag value at the start is 0. Okay. So it checks for flag value equal to 0, equal to 1, and it sees that this condition is not correct. So it will exit the loop and make flag equal to 1. But before it can go ahead and make flag equal to 1, there is a context switch here at this moment. So this flag has read the value, so this thread has read the value of flag, which is equal to 0, compared it to 1, concluded that 0 is not equal to 1, so this condition is false, has exited the while loop, but has not yet made flag equal to 1. Okay, so the original value in RAM for flag is still 0, and there's a context switch at this point. Thread 2 runs, it also calls lock. Okay, again, it will read the value of flag from RAM, which is still the original value 0. It will see that this value is not equal to 1. It will exit the loop, make flag equal to 1, and return the lock function. Lock function will return, and thread 2 will enter its critical section. Okay. Thread 2 has entered its critical section, and let's say there's a context switch again. Thread 1 is rescheduled, and it will continue its execution from where it left off. Remember, it had concluded that flag is equal to not equal to 0. Flag is 0 and not equal to 1. It had exited the while loop, and it was going to set flag equal to 1. Okay. So it's going to set flag equal to 1 based on the old information that flag was 0 at that time. Right now, flag has already become 1 by thread 2. So since thread 1 is not aware of it, it will also set the flag to 1. It will return the lock function, and thread 1 will also enter its critical section. So right now, two threads are in their critical sections, thread 2 as well as thread 1. Okay, so mutual exclusion has been violated. Okay, if you see the code here, thread 1 basically sees flag 0 not equal to 1, it breaks the loop, and before it can set flag to 1, here there's a context switch, and thread 2 runs. Thread 2 again reads the value of flags equal to 0, sees that it's not equal to 1, exits the loop, make flags equal to 1, and returns from the lock function and enters its critical section. Okay. While thread 2 is in its critical section, there's a context switch again. Thread 1 is rescheduled, and thread 1 will continue its execution from here. It will erroneously think that flag is still 0, so it will make flag equal to 1 and return from lock function and also enter the critical section. So two threads in the critical section simultaneously is a violation of mutual exclusion, and it would basically this implementation also is not correct. That was for a single core processor. Let's say our multi-thread program is running on a multi-core processor. Okay. So again, there can be a scheduling where two threads running on two different processors call this lock function simultaneously. Okay. So initially value of flag is 0. Since this function is called by both threads simultaneously, both threads will read the value of flag, which is equal to 0. Both will compare it equal to 1. Both will conclude that it is not equal to 1. So both will, this condition is false. So both will exit the loop. Both will make flag equal to 1, and both will enter the critical section simultaneously. Okay. So again, a violation of mutual exclusion. Okay. So this implementation, which on the face of it seems very correct, is again not correct. Okay, and violates mutual exclusion. Okay. So it fails on the parameter of correctness. On performance also, it's kind of fails because the implementation of wait here has been implemented by spin waiting. Okay, so if we see here, the wait condition here has been implemented by this spin waiting while loop does nothing. Okay, so this will basically, this thread is doing nothing, and still it is running on the processor. So if it is allotted a quantum to run, it will use its full quantum while doing nothing. Okay, so it will waste CPU time, and if you have hundreds of threads waiting for locks, they will be wasting a lot of useful CPU time doing nothing. Okay. So it's kind of on performance front also it has issues. So this was our second implementation, which also failed us. So we basically in this third implementation, we will use some hardware support. Okay, so the hardware support makes implementing this locks very easy. So let's say you have your instruction set in which you have different instructions in architecture in the processor, like we saw in a few videos earlier, this move instruction, add instruction, etc. These are assembly instructions which are part of our processor's instruction set architecture. So let's say we have this single instruction in our instruction set of our processor, which is called test and set. Okay, atomic exchange. It's also called atomic exchange. So this instruction, if it is included in our instruction set at assembly level, then we see how we can use this instruction to achieve the implementation of locks. Okay. So what does the test and set instruction do? This is the C code of the functionality of the test and set instruction. Okay, but remember the test and set instruction is not a C code, it's a binary instruction implemented in hardware. Okay, so it's only one instruction, assembly instruction, but here we are just to show the functionality of this instruction, we have written this C function. Okay. So this C function is just to show you guys how the instruction works. Actually, this is a binary assembly level instruction which is implemented in hardware of the processor. So what the test and set instruction does is that it takes two arguments, a pointer and a value, address, a memory address, and a value new. So what it will do is it will store this new value at this memory address pointer. Okay, we are dereferencing this pointer to store this value new at the memory location pointed to by this pointer. So it will store this value at this memory address, and it will return the old value that was at this memory address. It will return or give us back the old value at this memory location. Okay? So that's why it's called exchange. It is taking the old value and replacing it with the new one, okay, at this address. It will return the old value to us in the processor. So this is basically reading a value, returning this old value, and writing this new value to the old to the pointer address. And this exchange is basically done at assembly level atomically. Remember, an atomic operation is something that either happens completely or does not happen at all. So when this instruction is executed, it is executed atomically, which means if this either it is executed successfully or it is not executed at all. Okay, so if it is executed successfully, that would mean after its execution, the new value would have been written at this address, and the old value would have been returned to us. It cannot be interrupted in the middle. It's an assembly level instruction. It is executed atomically, either completely or none at all. Okay. So I hope the functionality is clear. It takes a pointer and a value. It writes the value to the location pointed to by the pointer, but before writing it, it will return us. It will store the old value and return the old value to us. Okay. So let's see how we can use this test and set instruction to implement lock. So again, our lock structure is similar to our last implementation. It has only one value called flag. So in it is the same. It will initialize the flag to 0. 0 means lock is available and 1 means lock is held. So in the lock function, instead of simply reading the variable like we were doing in the last implementation, we are basically doing the operation of test and set on this variable. Okay. So remember, test and set took an address. So here the address is of this flag variable inside the lock. Okay. So we give it the address of the flag variable and we give it this value 1 as new value. Okay. So what test and set would do, it would basically write this new value at this address. It will store 1 in variable flag and return the old value of the flag. Okay. So the old value of the flag, if it is equal to 1, it means the lock was being held and we do nothing and we spin, wait. Okay, so if the old value returned is 1, it is being, we spin because old value is telling us that lock is being held by some other thread right now. When that thread would release the lock, it would write 0 in flag. Okay, so release would write 0 in flag. So if we are waiting for that lock in this test and set, we are giving it 1 to write, and test and set is returning us the old value. So if the value returned by test and set is 0, it means the old value of the flag was 0. The flag was the lock was free. So 0 is not equal to 1, and we can get out of this while loop and return the lock function. So whoever thread had called this lock function was waiting for the lock to be free. Now its lock function will return and it can continue its in critical section. Okay. And the old value of the flag was 0, so we acquired the lock, but while acquiring the lock we also wrote this new value to the flag. Okay. And this has been done atomically. So now the flag value has become 1. Okay. And our thread is holding the lock. Meanwhile, if another thread basically tries to acquire the lock, it will block because its test and set will return the old value of flag as 1, and as long as this old value is 1, the lock function will spin and the thread will wait for the lock to be free. Okay. So now let's think in terms of if multiple threads basically try to call this lock function together on multiple processors. So in that case, let's say 2 threads called lock, they both will call test and set. Okay. And test and set basically both will be trying to write value 1, and we know that test and set is an assembly level instruction that will be executed atomically. Okay. So it will either be executed in entirety or it will be executed none at all. So if 2 threads basically call this test and set simultaneously on 2 different processors, then the value of flag is in RAM. So both of these processors will try to write this value 1 on flag. Since there is only one RAM, only one of those processors will get access to the variable flag in RAM and will be able to complete this operation successfully. Okay. So whoever gets access to RAM first will write 1 in the flag instead of 0 and will be able to acquire the lock, and whoever gets access to RAM second will see that flag is 1 because its test and set will return 1 as old value because the value on the first thread wrote 1 when its test and set was executed. Okay. So since test and set is atomic, it will complete first for only one of the processors, and the second processor would not be able to acquire the lock and it would spin. So this is an implementation of locks which will work correctly on single core processors as well as multi-core. Okay, so kindly think about it. Imagine different scenarios where multiple threads are trying to acquire the lock, and context switch can happen anytime in case of single processor or multi-core processor. In multi-core, you can also imagine different threads trying to do different things in parallel, and try to see if this implementation fails the parameter of correctness in any given scenario. Try to imagine and see what happens. So this is an implementation of lock. Only one of the threads will be able to acquire the lock. For all others, lock function will block and the thread would spin and wait until lock is released and they acquire the lock. In unlock, we simply free the lock by writing 0 in the flag. So as I said, think about it in terms of correctness in different scenarios, and think about performance. Again, we see here that the waiting is done by spin waiting. Okay, so all the threads that are waiting for the locks will be spinning and executing on processors, wasting their time quantums, doing nothing. Okay, so it's not so good in terms of performance and fairness. Again, there's no concept of fairness in this implementation. Okay? Fairness basically guarantees that every lock thread should get access to lock sometime. So this is one implementation of locks. Different our processors have different kind of instructions. Okay, so again, locks also could be implemented using different types of instructions. So in our last example, we saw a special instruction called test and set, which was used to implement the lock. Here, let's say on another processor, we have another instruction which is called compare and swap. And this time we'll try to implement locks using this compare and swap instruction. So compare and swap, again, here it's C code to explain its behavior, but actually this instruction would be one instruction in assembly and it would be executed atomically. Okay, so C code is just for explanation of the working. So compare and swap basically takes three parameters. First is an address, the second is an expected value, and the third is the new value that you want to write at that address. So basically it takes the address and stores the old value at that address in actual and see if the old value at that address is equal to the expected value. Remember we call expected value here. So if the old value is equal to expected value, only then it will write the new value at this address. And it will still return the old value to us. Okay? So it's kind of similar to test and swap, test and swap or test and exchange. What was it? Test and set. It's similar to test and set, except that test and set wrote this new value to this address irrespective of the old value. Here, compare and swap basically writes this new value to this address only and only if the old value is equal to this expected value that we pass. Okay, so it's not so different from test and set. In both cases, we are writing this new value and getting this old value back to a return value, and this operation happens atomically. So let's see how compare and swap could be used to implement locks. Again, the lock function is similar to test and set. We get a lock and we compare and swap, give it the address of the flag, expected value to be 0 and new value to be 1. Okay? And it returns the old value which we compare to 1. Okay? So if the old value of the flag was 1, if the old value of the flag was 1, then it will basically store the old value which is 1 here in actual, and it will compare the actual old value to expected value. Expected value we are passing here 0. Okay? So old value is 1, which is not equal to expected value 0, so it will skip this storage and return the old value which is 1. Okay, so as long as old value is 1, we are basically spinning, waiting. Okay? Because old value of 1 means the lock is being held by some other thread. So as soon as the old value becomes 0, the value of flag becomes 0, then when we call this compare and swap instruction, it will see again execute this old value here in actual. Old value, remember, is now 0. So it will compare old value to expected value. So expected value is 0. This condition is true. So it will store the new value at this address and return the old value. Okay? So it will write 1 to this flag, which will basically say now that our thread has acquired the lock, and it will return the old value 0. So here we see that the compare and swap returned the old value equal to 0, which is not equal to 1. So this loop condition will become false, this loop will exit, and our lock function will return. Okay, and we can enter the critical section. So this is the implementation of lock using compare and swap instruction, okay? Similar to test and set. We don't study the unlock or release function because it's the same. We just write 0 to flag. The interesting part is this lock or acquire function. So yeah, again it is using spin lock. So it's same in terms of correctness and performance to the test and set implementation. This is a third way to implement lock. So some processors, they do not have these test and set or compare and swap instructions. Instead, they have these other special instructions which are load and store instructions, similar to load or store instructions, but behave differently. So these instructions are called, they are pair of instructions. They are called load linked and store conditional. Okay. So load linked is load instruction, as the name indicates, but it's a special load instruction. It's different than normal load instructions. Normal load instructions, if you remember, loads value from RAM into a register. This instruction will also load a value from RAM from this address into some register. Okay, it will return the value stored at this address. But it's different from the normal load instruction because it is linked to the store conditional instruction. So internally, the operating system keeps a record of that a load linked instruction was performed to this address. Value was loaded from this address using load linked instructions. So after that, when a store conditional instruction is executed, store basically takes a value from a register and stores it at an address in RAM. So store basically takes an address and a value that you want to store at that address. So store conditional basically will store this value at this address if and only if no update to this address has been made since the last load linked instruction was made to this address. Okay. Remember, for load link, the processor is storing a record that a load link was performed at this address. So if since the last load linked operation on this address, no other action has been performed on this address, then this condition will become true and the store conditional instruction will store this value at this address, okay, and return 1, success. And if there was an intermediate operation on this address between the load linked was performed and before store conditional was performed, in that case this condition will become false and it will go into the L position and return 0, which means store conditional was failed. Okay. So load linked and store conditional, they are a pair of instructions. They operate in tandem, like in synchronization with each other. And after a load linked to an address, a store conditional to the same address would succeed only if between the load linked and the store conditional no other update was performed to this address. Okay. So if this condition is true, then the store conditional will store this value at this address and return successful. Otherwise, it will return failure. So let's see how load linked and store condition can be used to implement locks. Again, store condition only succeeds if no intervening update has happened to this address since the last load linked. Here is an implementation of the lock function using load linked and store conditional operation. So this lock function is used to acquire the lock. Okay. In it, we have an infinite loop. Okay. So it will basically perform a load linked on the address of flag, which means it will read the value of flag using this load linked instruction and compare it to 1. Okay. So as long as the flag value is 1, we are spinning, we are waiting, okay, because flag value of 1 means the lock has been acquired by some other process. We are waiting until that process releases the lock. So let's say that process releases the lock and load linked, so basically release the lock, that thread will write 0 in flag. Okay. So our thread, which was waiting for the flag to become 0, it will read the value of flag using load linked it will now receive 0. It will see that 0 is not equal to 1, so it will break this waiting loop and come here. And after this load length, it will now try to perform a store conditional on the same address that it read the value from using load length flag address. So it will try to remember the load length told us that flag value was 0. Okay? So flag value was 0, and now we know that flag is free, lock is free. So we are trying to acquire that lock by storing the value of 1 by writing 1 to the flag address by using store conditional. And store conditional will return either success or failure. So if since we read the value of flag as 0, from that time until the store conditional, if the value has address of flag has not been touched, the value has not been modified, then the store conditional will succeed. It will write the value 1 at this address and return success. Okay, and our lock function will return. Otherwise, if the last time we read this flag as 0 using note linked, and between the store conditional instruction, let's say there was a context switch and some other thread came and modified the value of flag. So when we resume and try to write 1 on this flag address using store conditional, because of its implementation, it would realize that there was an update to the flag address between the last load linked and this store condition instruction. Okay, so instead of going into this if condition, it will go, this condition will fail and it will go to else and return 0. Okay. So since there was an update to flag address between the load length and store conditional, so store conditional will fail and it will return 0. It will return 0 and this condition will become false and this return will not be executed. Okay, so we'll skip this return, come back here, and it's an infinite loop. We'll go back and get stuck in this load linked again. Okay, so now the flag has been modified, so we will have to reread the flag and wait for it to become 0 so that we can again try to acquire the lock. Okay, so in this way, load linked and store conditional instructions operate in combination, in parallel, in tandem to acquire locks. Okay, so this lock function will return only if we read the old value of flag to be 0, and then we are able to store the value 1 in flag. Okay, and in between no other thread has modified the value of flag. Okay, so basically we saw that flag value was 0, lock was free, so we acquired the lock by using writing 1 to the flag, and then if successful, our lock function will return and our thread will enter the critical section. Okay? And while we are holding the lock, any other thread which tries to acquire the lock will basically wait, spin wait. And releasing is just writing 0 to flag. Again, this was an implementation of locks using load linked and store condition instructions. Another implementation. Again, some other processors have other instructions in their assembly language which we can use to implement locks. One of those instructions is fetch and add. So fetch and add again is an assembly level instruction, is executed atomically, is implemented as hardware inside the processor. Okay, but here we have the C code to show us the behavior of fetch and add. Fetch and add basically takes an address, it updates the value at that address and returns us the old value at that address. Okay, return type is an int, it returns the value. What does it return? It returns the old value at that address and the new value at this address is incremented. Okay, so again the name fetch and add, it will fetch the old value and add or increment the value at that address. Okay. So how do we implement locks using this fetch and add instruction? Okay, so this implementation is slightly different. In it, the lock structure contains two variables. two integers. One is called ticket, other is called turn. Initialize, when we initialize this lock, we initialize ticket and turn both to 0. So the lock function, whenever a thread calls a lock on that function to acquire the lock, it will first perform fetch and add on the address of ticket. So it will fetch and add. Fetch and add, remember, it returns the old value at this address and increments the value at this address. Okay. So initially ticket was 0, and so fetch and add will basically return 0, and at the same time increment the value of ticket, which means in RAM the new value of ticket will become 1. Okay, so now the value of ticket is 1, and it returned us the value of old value of ticket, which we have stored in this value my turn. So now this value my turn is being compared to the value turn in the lock. Okay. Lock also has a variable called turn. So if my turn is not equal to lock turn, the turn in lock, it means it's not our turn. So we'll spin. We'll spin and wait until it becomes our turn. Okay. And once this value of lock value of turn becomes equal to my turn, then this condition will become false and we'll exit this loop, and our lock function will return and we can enter the critical section. The unlock or the release function just increments the value of turn. Okay. Lock value turn, all values incremented by 1. So if you see here, the lock value of turn is basically telling different threads whose turn it is to enter the critical section now. Okay. And ticket is basically just like you go to a bank and they give you a ticket. Ticket is basically your turn. That your turn is like 23. Okay. So ticket gives you your turn, which is like 23, and then you wait for this value lock turn to becomes equal to your turn. Okay, so when the lock arrow turn becomes 23, it means your turn has come, and now you can enter the critical section. Let's imagine two threads now. Two threads, they call lock and unlock in their while entering that critical section. So initially ticket and turn both are 0. So thread T1 calls lock. T1 calls lock, it will basically do fetch and add. Fetch and add will basically increment the value of ticket to 1, and turn will not be changed, turn will be 0, and it will return the old value of ticket in my turn. Okay, so my turn is old value of ticket, which was 0, so my turn is 0. So this thread T1 will basically look at lock arrow turn, which is 0 initially, and my turn, but they both are equal, so this condition is false, and this means that my turn has come. Okay, so this thread will see, okay, my turn has come, so it will exit this loop and lock function will return and it will enter the critical section. While it is in critical section, let's say thread T2 calls lock. So thread T2 calls lock. It will again do this fetch and add instruction. Fetch and add will basically increment the value of ticket and return the old value of ticket. So old value of ticket now was 1. So it will increment the value of ticket to 2, and my turn will receive the old value of ticket, which was 1. And then it will see that lock arrow turn is equal to my turn or not. Lock arrow turn is 0. Okay, it was 0 in the start and still 0. So it is not equal to my turn, which is 1 for this second thread. Okay, so this condition is true, and second thread would wait. It will wait until its turn comes, or lock arrow turn becomes equal to my turn. Okay, so my turn is 1 and it is waiting. Meanwhile, let's say a third thread comes and calls lock. It will again do fetch and add. So it will increment the value of ticket, which is 2, to 3, and return the old value, which is 2 in my turn. So the third thread would again check that value of lock turn is not equal to my turn. Okay, because turn is lock arrow turn is 0 and my turn is 2. So again this thread condition will be 2, and third thread will also wait. Okay. So both second and third thread are waiting. For second thread, my turn is 1, and for third thread my time is 2. So the first thread, which was in the critical section, after finishing the critical section, it will basically release the lock by calling unlock, and this function would increment the value of turn by 1. Okay. So lock arrow turn was 0, and after releasing of the lock, it will become 1. So after this value become 1, both second and third thread, which were waiting for this my turn to come, the second thread would see that now lock arrow turn has become 1 and my term is also 1. So it will see that my term has come and it will exit this loop and lock function will be returned, and the second thread would be entering the critical section. The third thread was also waiting for the lock. It will see that my lock arrow turn has become 1, but my turn is 2. Okay, so it will see that my turn has still not come. So it will continue spinning and waiting for the thread or turn to become its turn, okay, which it will get because after finishing the critical section, the second thread will also release the lock, increment the value of turn, and then value of turn will become 0, and then the third thread would be equal to enter the critical section. So this is how lock can be implemented using fetch and add instructions. So here again, if you talk about correctness, hopefully you if you imagine different scenarios on single processor, multiple processor, you will be seeing that this implementation is correct. And for waiting, again, this implementation is using spin lock for waiting. So performance wise, it will not be too good. But one other criteria where this implementation is good is that fairness, because as threads come and start waiting for the lock, every thread will get a turn. Every thread will get a turn, and the value of the lock arrow turn will be incremented one by one. Okay? So it will become equal to each thread's turn eventually. Okay? All threads waiting for the lock will eventually get the lock. Okay? So in terms of fairness, this scheme is better than others. So again, one other thing is with performance, all these threads, we have achieved correctness, we have achieved fairness to some extent, but there is still a problem with performance that all these threads, when they are waiting for the locks, they are basically spin looping and needlessly wasting CPU cycles. So what can be a more efficient approach to implement locks so that we don't waste CPU cycles? Again, this requires some OS support. One implementation would be that when a thread sees in a lock that lock is busy, okay, so instead of waiting or spinning in this loop, it can yield the CPU. Yield, if you remember in those CPU scheduling, we studied that there are cooperative approaches to release or sharing CPU between processes, in this case threads. So yield is a system call where a thread or a process tells the operating system that I don't need the CPU now, right now. Okay. So yield will basically make the OS deschedule this thread. Okay. It will, since this thread is going to wait anyway, so it yields its quantum of CPU and tells the OS that I don't need the CPU now, you can give it to somebody else. So the OS can deschedule this thread and reschedule another thread at this place. Okay, so it will cause context switch, but at least the busy waiting would be avoided. And then when this thread is rescheduled again, it can again test for flag and see if the flag is lock is available. It can acquire the lock. Otherwise, if it is still busy, it can again release the CPU by calling yield. Okay. So this, in this case, whenever a thread is scheduled, instead of wasting its full quantum, it sees that the lock is busy and foregoes the CPU and yields the control to the OS to give it to some other thread. This is some improvement on that. Threads don't spin unnecessarily, so some CPU time is saved. Another approach is to use queues inside the locks. Okay. Whenever a thread is basically waiting for a CPU, instead of making it spin unnecessarily, we maintain a queue inside a lock to tell which threads are waiting for this lock, okay, and put those threads to sleep. So since those threads would sleep, they will not be scheduled, so they will not be releasing CPU time, wasting CPU time. Okay. So any thread, if a lock is busy, any thread that tries to acquire the lock is put on this queue and put to sleep. Okay. When a thread releases the lock, then the operating system sees in this queue, are there any threads waiting for this lock? And if in this queue there are threads waiting for this lock, then the operating system can wake one of those threads and give the lock to that thread. Okay. So again, this is slightly complex but more efficient implementation in terms of performance, because all the threads waiting for the lock are not spinning unnecessarily, but they are sleeping. Okay, put on a queue and put to sleep. And one by one, when the locks are released, one of these threads are awakened and the lock is handed over to them. So in this implementation, inside the lock structure, we have this flag, we have this guard, and we have this queue. Initialize function would put this to 0 and initialize this queue to empty queue. So the lock function, it will basically first acquire this guard variable. Guard variable is to provide access to the lock structure. This lock structure, in this we have three different variables. We have to set the flag, we have to set the guard, we have to add elements to the queue. So all these operations, they should be performed atomically. Okay, so we should control access to this lock structure so that only one thread can modify this lock structure at any given time. For that, we use this guard variable, and the lock, we first test and set the guard variable to acquire the guard so that we can access this lock structure. As long as the old guard variable value is 1, this means some other thread is accessing this lock structure right now. So we wait until that thread has finished accessing the lock structure and make guard 0. Okay. So when that thread makes the guard 0, our test and set will succeed and it will return as 0 as old value, and we'll get out of this loop. Okay. So we'll see if the lock is free or not. If the lock is free, then we acquire the lock, release the guard, and get out of this lock function. But if the lock was busy, lock was busy, so flag was not equal to 0, flag was equal to 1. Flag was equal to 1, so we come in else, and this thread, instead of letting it needlessly spin, we would add this thread to the queue of this lock. This is lock M, and we will add to its queue this thread to tell the OS that this thread is now also waiting for this lock. So once the thread is added to the queue, we release the lock and we put this thread to sleep. Park, let's say it's a system call that puts thread to sleep. So this thread has been added to the queue of the lock and it will sleep and it will not spin needlessly. Unlock, when some other thread releases the lock, it will again first acquire the guard because it's need to modify the lock structure, and then it will see that the queue is empty or not. If the queue is empty, there is no other thread waiting for the lock, so it will make flag equal to 0 and make the lock available to everybody. But let's say while releasing the lock, this thread sees that there are some other threads that are waiting for this queue, for this lock, and they are on this queue. So what it will do, it will unpack. Unpack means it will remove the first element from the queue. One thread, it will remove it from the queue and it will unpack it. It will wake it. Okay, that thread was sleeping. It will wake it and it will make the guard 0. Okay. So the second thread, now that it is woken, remember the second thread went to sleep here. The second thread, has been woken, and now it will continue its execution from here. It will exit the lock function will return, and it will enter its critical section. Okay. So the flag is still 1. The flag was not made to 0 here. The flag was 1 when this thread was releasing the lock, and the flag is still 1 when this thread has entered the lock. So in a way, the lock has been passed from this releasing thread to this thread. Okay? So this thread eventually, it will also finish the critical section and it will release the lock. Again, it will see if there's nobody in the queue, it will make flag 0. Okay. Otherwise, if there are other threads in the queue, it will wake another thread and pass on the lock to that thread. Okay, and that thread will then be woken and it would go to in its critical section. Okay. So this is another implementation of locks, which is also ensuring correctness, fairness, as well as performance. Okay. Because here the waiting threads are not needlessly spinning, but they are put to sleep. So again, this is basically what we have discussed in the last slide. This is summarizing the functionality of this implementation. So this is the last section in this chapter. You are invited to read and try to understand this code yourself. This is on Futexes. Futex is basically the Linux implementation of locks or mutexes. Try to see if you can understand this code. Okay? And if you any questions, you can always ask me next week in the office hours. So this is implementation of Futexes, and then there is another section, a small section on two-phase locks. In two-phase locks, if a thread tries to acquire a lock, instead of if it sees that the lock is busy, instead of going to sleep immediately, it tries to spin for a while to see if that lock is released in near future. If it sees that after spinning for a while, it sees that lock is not being released, so it assumes that okay, lock is busy for a long time, so then it goes to sleep. Okay, so it's just like our last implementation that we studied, but instead of going to sleep immediately, it first tries to spin to see if the lock is released soon. Okay, so if it is lucky, lock will be released soon and it will acquire the lock immediately. Otherwise, if it sees that lock is busy for a long time, then it will go to sleep. So that's the acquiring is done in two phases. First, it tries to spin, and if it still doesn't find the lock, then it goes to sleep. That's why they're called two-phase locks. They are slightly, the thinking behind this is that sleeping and context switching is expensive. Okay, so we can, before going to sleep, we can spin for a while to see if lock is available immediately. So that way we will avoid the sleep operation and context switching. So this is two-phase locks, and this basically concludes our chapter on locks. So I'll stop this recording and you guys can read, listen to this video and try reading the book to see how much you understand. Thank you very much.